All right, when I'm moving forward, my vehicle has kinetic energy. When I want to come to a stop, the kinetic energy has to go someplace. Now, the way I make it go away is I pull the brakes. That makes friction between some discs and some pads. And the friction is the agent by which my kinetic energy is reduced. Where does the energy go? Thermal energy. And where is the thermal energy? In the discs and in the pads. We can see that. Let's take a look at the thermal camera. We have a view in the visible light, and now a view in the infrared. And you can see the discs. They're pretty toasty. All the kinetic energy of my forward motion turned into thermal energy in the discs and in the pads. And that relates to the problem that we're going to look at today. Let's take a look at the problem. Your car has a mass of 1,600 kilograms, including the mass of the fuel and driver. You are driving at a constant speed of 20 meters per second on a level road. The road descends, dropping 32 meters into a valley. As you drive down the slope, you press on the brakes to keep your car moving at a constant speed. How much thermal energy is deposited in your car's brakes? Now, this is an energy problem, as we talked about before. But let's take a look at the important data in this problem. First off is this piece right here. Your car has a mass of 1,600 kilograms. And that includes you and the fuel and everything in the car. So that's going to be the mass that we need to work with. We're told that you're driving at a speed of 20 meters per second. But the most important fact about your speed is this, that you're driving at a constant speed. Okay? What constant speed tells us is this: your kinetic energy is constant. And since we're solving this as an energy problem, that's going to be important. As you're driving, the road drops, and it drops by 32 meters. Now that's clearly going to be important to us because as the road drops, what form of energy is changing? Potential energy. So that's a piece that's going to be interesting. Now let's look at what we're ultimately interested in solving for. It's this: how much thermal energy is deposited in your car's brakes? Now, in fact, all the thermal energy will end up in your car's brakes, as we saw. So we just need to calculate how much energy in this process is converted to thermal energy. It all ends up in the car's brakes. So really what we want to know is this: how much thermal energy is left at the end of the process? Let's look at how to solve that. The first piece of the puzzle is going to be to draw a before and after visual overview. So here's our slope. And the before is the initial state of the car. We have a car at the top of a hill, and the car is moving forward at 20 meters per second. The car goes down the hill. At the end of the problem, the car is at the bottom of a hill, and the car is still moving at 20 meters per second. We're told that the speed stays the same. The speed is constant in the problem. So we have our two states of the system. We have our before case, which is right here at the top of the hill, and we have our after, which is right here at the bottom of the hill. Now let's think about the in-between piece on the slope right here. Energy is being transformed from one form to another. But what energy transformation is taking place? The car is moving at a constant speed. It's rolling down the hill. You are pressing on the brakes to keep the car moving at a constant speed. As you do this, what energy change is taking place? Here's some choices. We're looking at a situation where the car is moving down the hill at a constant speed. Since the car is moving at a constant speed, the kinetic energy is constant. What's changing here is the potential energy. The potential energy is decreasing as the car moves down the hill. Well, if the potential energy is decreasing, kinetic energy is not increasing. The extra energy has to go someplace. Where is it going? It's going into thermal energy in the brakes. That's why you have your brakes on. As the potential energy decreases, the thermal energy increases. Kinetic energy stays constant. Let's sketch out the problem again, and let's do our before and after states in some detail. We said we've got two states. We have the car at the top of the hill, and I'm just going to draw a simple representation here. And at the top of the hill, that's our initial state. We've got a certain initial kinetic energy, and I've got a certain initial potential energy. And we're interested in gravitational potential energy. There's no spring potential energy here. Okay? At the end of the problem, the car's at the bottom of the hill, I've got a certain final kinetic energy, and I've got a certain final potential energy. What's ultimately important about the kinetic energy is this. The initial kinetic energy and the final kinetic energy are equal to each other. So these two numbers, we don't care so much what they are. We just care that they're the same. Now, the initial and the final potential energies are another story, and they do change. And remember, gravitational potential energy is generally equal to mass times g times the height. So we're going to need to specify for the initial position and for the final position, what is the initial height, yi, and what's the final height, yf. Let's specify those. We'll give you some choices. It's important to have a reference in the problem for your vertical positions through potential energies. And it makes sense to call the final position, where the car ends up, to call that 0 meters. So our yf, our final position, is just equal to 0 meters. Our initial position, that's at the top of the hill, and we're told that the car drops 32 meters as it goes into the valley. So our initial position, our initial height above the valley floor, that's 32 meters. So we know that kinetic energy is unchanged. We know our initial height. We know our final height. We know how to calculate potential energies. We're ready to do some calculation. We're going to use our basic equation for calculating energy changes. And we'll use the one that has thermal energy in it because we know there's friction. And our equation looks like this. The final kinetic energy plus the final potential energy, and that's a gravitational potential energy, plus the change in thermal energy is equal to the initial kinetic energy plus the initial gravitational potential energy. That's our basic equation. Now we can make some simplifications here. The most important thing we can say is this. The initial kinetic energy and the final kinetic energy are the same. So we can take those terms out of the equation. We don't need the kinetic energies. So then our equation reduces to something which is much simpler, which is this. The change in thermal energy is equal to the initial potential energy minus the final potential energy. And that makes sense because we said as the car was going down the slope, what was changing was that potential energy was being converted into thermal energy. So this result makes a lot of sense. Now we're ready to put in some numbers. We'll rewrite the equation. So our change in thermal energy is equal to our initial potential energy, but we're going to write this as m times g times yi, because we know that's what the potential energy is, minus the final potential energy, which is m times g times yf. And now we can use the values for the initial and the final positions. The initial height was 32 meters. The final height was 0 meters. We can also substitute values for the mass of the car, plus the fuel, plus the driver, 1,600 kilograms. And we can put in a value for g, 9.8 meters per second squared. That gives us everything we need to solve the problem. And if we do it, we can substitute numbers, and we calculate to two significant figures a final answer of 500,000 joules. Let's take a look and see if that makes sense. Last piece of the puzzle. Let's look at our answer and see if it makes sense. We got 500,000 joules. That's a lot of energy. That's enough energy to take the 2 kilograms of liquid inside this bottle and raise it from room temperature to almost the boiling point. But it's not a surprise that we'd have a lot of energy. You have something which has the mass of a car that's pretty heavy, and it's descending from a height that's approximately 3 times the height of the building behind me. All that energy goes into thermal energy of the brakes and the pads, which is why the brakes better be made out of a material that can handle high temperatures, as we know they are. It's not a surprise. Physics is about the world around us. All right.